evaluate this definite interval. So we're going 0 to 2, x plus 4 over x squared minus x minus 6. So that's one polynomial over another polynomial. That suggests to me to use a partial fractions decomposition. Okay, let's give it a try here. So first we got to decompose x plus 4 over x squared minus x minus 6. And if we're going to use the partial fractions decomposition approach, we do need to have the denominator factored as far as we can. So, how do I factor this? So I need two numbers that multiply to -6. So numbers that multiply to 6 would be 1 and 6, 2 and 3. Do any of them have a difference of 1? Right? So 3 and 2. Right? So we get a 2 and a 3. Now, -3 and +2, that gives me a sum of -1 and a product of -6. So there we go. And now that we have the denominator factored, we set up the form of our partial fractions decomposition. We introduce constants. These are real numbers, a and b. And we can find the right a and b to make this equation true for all values of x for which both sides are defined. Okay, so how do we do that? Well, what we're going to do is we're going to take our expressions here. So we got a over, I did x plus 2 first, yeah. And we're going to multiply both sides by the denominator here. Okay. X plus 2, x minus 3. X plus 2, x minus 3. And so the x minus 3's cancel out, and so do the x plus 2's cancel out over here. So we're just left with x plus 4. Just a factor of x plus 2 cancels out here. So we've got a times x minus 3. And then b will be left with just x plus 2. Okay? So now this equation needs to be true for all values of x. So we can rely on that. And if we just want to isolate a and b by themselves, okay, what we could do is we could look at these linear factors. What makes x minus 3 equal to 0? Well, a value of x being equal to 3. So if we let x be 3, we'll get 3 plus 4, which is 7 over here, a times 3 minus 3 plus b times 3 plus 2. So that's 7 is equal to 0 times a, well, that's just 0, plus, and then 5b. So 7 is equal to 5b. That gives me the value of b. It's 7/5. Fantastic. Okay. We can do the same sort of trick again. X minus 2. What would make x minus 2 equal to 0? Well, if x was equal to -2. So let's try that out. So we get -2 plus 4 on the left-hand side. A times -2 minus 3 plus b times -2 plus 2. But that's going to be 0. -2 plus 4 is 2. And then we get minus 5 a's. So a is going to be -2/5. Right, so we've got our b value is 7/5 and a is -2/5. Okay, so that gives us our decomposition, our partial fractions. So this is an alternate way to express x plus 4 over x squared minus x minus 6. So the a value, so 2/5 over x plus 2, and then 7/5 over x minus 3. All right. How does that help? Well, by rewriting this integrand, we can more easily integrate. So we did have x plus 4 there, but now if we replace that, x plus 4 over x plus 2 times x minus 3, with our separate factors here, we can then split things up a little bit. I usually take the constants out, unless they're particularly nice. Okay, and now we can integrate these. Okay. So if we need to go slow, we can do a substitution to integrate this to ln absolute value of x plus 2. And we can integrate this to ln absolute value of x minus 3. Do be careful. It's not just ln of whatever's down here, because if it was 2x minus 3, you'd need a 1/2. So if you're at all worried about something like that, always do the substitution. You know, you just let u equal whatever the denominator is. Okay. But continuing on, minus 2/5 plus 7/5 there. And then plus a c, because I've got a definite integral symbol here, but we don't really need the plus c, because ultimately we're trying to evaluate a definite integral, not an indefinite integral. Okay. So now I think we were going 0 to 2. Yeah, 0 to 2. So now we have enough information to actually answer the question. And we'll write the original question here, why not? Okay, so we take our negative 2/5 ln absolute value x plus 2, okay, plus 7/5 ln absolute value x minus 3. And we'll evaluate that at 0 and 2, and we'll take the value at 0 away from the value at 2. So minus 2/5 ln, plug in 2. 2 plus 2 is 4. Absolute value of 4 is just 4. So we'll just say ln of 4. Plus 7/5 ln, okay, now we plug in 2. 2 minus 3 is negative 1. Absolute value of that is just 1. So ln of 1. Which, if we think about it, ln of 1 is just 0. So we can actually ignore this part. Okay. Minus, and now we're going to plug in 0. So minus 2/5 ln 0 plus 2 is 2. And the absolute value of 2 is just 2. And then 7/5 ln 0 minus 3, which is absolute value of negative 3. But we can just write 3. Okay, so now, what can we do? Well, we can distribute this minus sign here. So we get minus minus, so that's plus 2/5 ln 2. And then minus times the plus here is actually going to give me minus 7/5. Where can we go from there? Well, let's see. We could take out a factor of 1/5 from everything. So we get minus 2 ln 4 plus 2 ln 2 minus 7 ln 3. And is there anything else we could do to combine these? Well, yeah, we know our logarithm properties, so we could do something like bring this 2 up inside as an exponent. And we've got minus 2 ln 4. 2 to the power 2 is just going to be another ln 4, so that's kind of nice. We get minus 2 ln 4s plus another ln 4 is going to give us minus 1 ln 4, or just minus ln 4. Minus 7 ln 3. Well, I suppose we could take out a minus sign. Make this minus 1/5. So ln 4 plus 7 ln 3, now that the minus sign has been taken out. And, well, you could probably get away with leaving it like that, but if you really wanted to, you could bring the 7 up. So get ln 3 to the power 7, which is, what was that, 2,187. And then add the 4. So I guess if you really must have everything as a nice simple logarithm, you get minus 1/5 ln 3 to the 7 times 4. And 3 to the 7, you can work that out and then multiply it by 4. 28. But this is a little bit of overkill, I would say, to do by hand. But there we go, 8,748. But that doesn't really give you any better sense of what's going on here. There's a very, very simplified answer, but something like this is fine. And I mean, the obvious thing is the ln 4s to cancel out, right? But there we go. There's our nice single condensed value.